Good morning, everyone. This is Xian Lu from Clemson University. This science highlight is about the importance of regional aurora, electric field variability, and ground wave to the storm time thermospheric temperature enhancement and inversion layer we call TTEIL in Antarctic E region. First of all, I want to thank my collaborators, Haonan Wu, who is my graduate student and did most of the modeling work, and other collaborators Gang Lu, Xinzhao Chu, Wenbin Wang, Zhibin Yu, Liam K. Commons, Dolores Knipp, Boyi Wang, and Toshi Nishimura. The motivation of this work is from the Aaron Borsman LiDAR measurements at McMurdo on May 28, 2011. The neutral temperature profile shows a significant temperature enhancement around 135 kilometers, then decrease with altitude, which forms an inversion layer. And for this particular event, there was a moderate storm with KP index equaling to 6 and a CME event. So we want to study the mechanism for the formation of the TTEIL for this particular event. And from the empirical models, if the IT model is driven by the empirical Aurora map, it's very difficult to capture such a localized magnetospheric energy deposition, and it's because the empirical auroras often miss the localized and also very large values of aurora energy and the mean aurora energy flux and the mean energy of aurora. So this figure is showing the SUSY observations from 1121 to 1143 UT on May 28th, and this is the corresponding aurora maps from the AMI without assimilating the SUSY observations. So if AMI assimilates SUSY observations, you can say it improves and it starts to show some features from the observations, but still AMI doesn't give us the enough resolution and value that we need in order to simulate the TTEIL for this particular event. So what we did is we used the SUSY observations directly whenever the observations are available. Then we put into the model, and then when the observations are not available, we do the linear interpolation to fill up the gaps. So you can see this map is showing the SUSY observations before linear interpolation, and this is after. And some other regions are filled up in this case. At the noon sector, there is no observation at all, so it does not pass that area. Then we used the model simulation of the aurora map. So this is the final aurora maps we used in TIE GSM that incorporates the SUSY observations. So by comparing with the AMI, we can say this method can actually better resolve some of the regional scales of the aurora, and some of them does show very large values that we need. Okay, so another modification we did is for electric field variability, because we know that Joule heating is related to electric field by E squared. So that's why fluctuations, variabilities of electric field also contribute to the overall Joule heating. And typically in TIE GSM, Joule heating is multiplied by a factor of 1.5 in order to account for subgrid electric field variabilities. But in reality, the variability of electric field, it does have a highly structured spatial distribution. The Cousins and the Shepard study showed that this is the ratio of electric field variability versus the background electric field. And you can say the large ratios of E prime over E naught follows the aurora shape. So what we did in the model is we only add electric field variability in the aurora region. And such variability is treated as a random process, but it does follow a certain statistical distribution, and we adopt exponential distribution coming from this study as well. And the ratio is chosen to be 1 in order to follow the statistical studies using observations. Okay, so then we have two configurations of aurora, and the two configurations of electric field. For Aurora, we can use the Aurora that tends to be more realistic because we incorporate the SUSY observations. So that's one setup. The other setup is AMI Aurora, even without SUSY assimilation at all. So AMI Aurora here is very weak. Then the electric field, we use AMI electric field. That's one configuration. The second configuration is we also add the variability of electric field, as I just mentioned in the last slide. And this is just the different combinations of these two different configurations. And only run 4 incorporates SUSY Aurora, and at the same time also adds the electric field variability. So when we compare the observations of neutral density from GRACE with model simulation, you already can identify the improvement from run 4. So run 4 is this red curve, and gray curve is the GRACE observations. And you can say run 4 best matches the neutral density observations by the GRACE. And all the other runs show significant underestimation of the neutral density. And if we focus on the neutral temperature, before 1140 UT, the temperatures from the 4 runs, they tend to bunch together and not too much difference between them. But after 1140 UT, you can see they start to separate, and the run 4 starts to show significant temperature enhancement and also the inversion in the lower thermosphere in this case. So this kind of implies that electric field variability and Aurora, enhanced Aurora, are both important in our simulation to produce TTEIL and neutral density as observed. So this is a structure of TTEIL in more detail. The feature lasts about 1.5 hours in terms of the time span. Then latitudinally and longitudinally, it tends to be a medium to large scale feature, spanning about 20 degrees in latitude and 80 degrees in longitude. So it's not a local feature. It's not a local feature. It tends to have a certain span in spatial. So we use the thermodynamic equation in TIE GSM to identify which thermal forcing term is most important in controlling the final shape of the temperature profile. And there are several terms in TIE GSM that contributes to the evolution of temperature. First is heat conduction. Second is eddy diffusion. Then we have horizontal advection, vertical advection, adiabatic cooling, heating term, diabatic heating, and diabatic cooling. We see that Joule heating is the most dominant term in the polar region for diabatic heating. And in this case, it penetrates down all the way to 120 kilometers, which is pretty deep. And we think part of the reasons is because we adopt the observed aurora from SUSY, which have large mean energy of aurora able to be implemented into the model, which cause the ionization rate to be enhanced in the lower thermosphere, in the E region, and causing the deep deposition of magnetospheric energy deposition into the lower thermosphere. Then accompanying to the strong Joule heating, there is also a strong upward vertical wind reaching magnitude of 100 meters per second. And we know that when the atmosphere goes up, it expands and cools down because of doing work to the environment. So adiabatic cooling is getting very, very strong above 150 kilometers. So at 120 kilometers, then you can see Joule heating is very dominant and is very strong. Adiabatic cooling starts to catch up, but still compared with Joule heating is kind of small. But when we go to 200 kilometers, because Joule heating at that altitude is not as strong as 120 kilometers, but however, the adiabatic cooling starts to catch up and it becomes significant. So down to 120 2130 kilometers, there is a net heating effect. But because of the adiabatic cooling above, then around 200 kilometers, there is a net cooling effect. So this induces a differential heating profile, which heats the atmosphere below and cools above, then causing the inversion layer. Then we can say vertical advection, however, it cools the atmosphere below but heats above, so which is kind of the opposite effect in terms of the Joule heating plus the adiabatic cooling. And this can be better seen when we study the integrated effect of specific heating terms. So specifically, if heating is only from Joule heating, then we can say there is a net heating effect. If it's only from adiabatic cooling, then there is a net cooling effect. But the peak is higher than the heating peak. So by considering only these two factors, we can actually have a very sharp and a big magnitude of inversion layer because of the huge heating down here but cooling above. So as I mentioned in the last slide, after we add the vertical advection, because the counteractive effect from vertical advection, you can say after we add vertical advection, that the TTEIL, the weight broadens, also the magnitude is weakened. When we add the other terms, it doesn't change too much. So which means that in terms of the TIE simulation, the most three important factors that contribute to the temperature profile is Joule heating, adiabatic cooling, and vertical advection. So when the LiDAR measures the temperature inversion layer at McMurdo, it's around 15 UT. Then we take a closer look at the DMSP measurements from SUSI and from CSIS. During 15 UT, close to 15 UT, Aurora is getting close to McMurdo. Usually McMurdo is far away from Aurora. Usually it's pretty far away from Aurora, but at this time it's getting close. And at the same time, an interesting thing is the electric field also shows a significant magnitude. The ion drift goes to as much as 3 kilometers per second, which is pretty big, and also associate with quite a bit of fluctuations. So after we implement this localized feature of Aurora and electric field into the model, we are able to get similar TTEIL structure as what we just shown earlier. But however, we still feel that we're not quite there yet, because if you compare the model simulations, the TTEIL, the peak, it's around 150 kilometers, but the observation is actually around 130 kilometers, and the waves is also narrower in the model. Is also narrower in the observations than in the model. In the model, the waves is much wider. So we think we learned something, but still, this is not the end of the story. And if we look at the temperature profiles, this large gradient looks like a wave. So then what we did is we also examined whether the possible effects from gravity wave. These two figures are showing the simulation of the TIE layer did by Dr. Xinjiao Chu and her student Zhibing Yu. In their paper, they need to, in order to simulate the wave signatures in the TIE layer, they added a gravity wave with vertical wavelengths about 30 to 50 kilometers is changing with altitude into their model, and around 150 kilometers, the amplitude of the wave in vertical wind is around 12 meters per second. So in principle, we can use the gravity wave polarization relation to infer the amplitude in temperature from the wave amplitude in vertical wind. And of course, this is a simplified version. We don't consider dissipation in this case. If we just by some simple calculation, so this would be a preliminary possibility that the same gravity wave added in their model could perturb the temperature like this. Around 150 kilometers, it will cause a temperature perturbation around 200 kilometers, assuming the background is already elevated to, say, 1000 Kelvin in this case. Then after we add the gravity wave perturbations into the background, the elevated background simulated by the TIE GSM. So this is TIE GSM simulated background. So if we superpose these two together, then we can see that the simulation starts to show better agreement with observations. So this maybe imply that electrodynamics and neutral dynamics, we would say wave dynamics, could play together and ultimately forming the TTEIL that's observed by the LiDAR at McMurdo. Okay, so we learned something from this study, but we also feel there are more things to be answered in the future. So let's talk about what we have learned. First of all, we kind of feel that to simulate the local IT system response to geomagnetic storm, the model drivers with local and regional scales for Aurora, for example, and for ion convection are desirable. Only when the local and the regional scales with realistic magnitudes are captured, then we are able to produce the observed features locally. So this is very important. And to do that, we think data assimilation combining ground-based and satellite data with multiple layers of resolutions for Aurora and ion convection may be necessary. So in this study, we only used satellite data from SUSI, but we know that there is also rich data set from THEMIS ground-based air glow images, which maybe we can combine them together and form up a better Aurora map to study the IT system response to storms. And from the TIE GSM, we figure out the forming mechanism of observed TTEIL is that the strong differential heating is important. We need heating locally in the lower thermosphere, around 120, 130 kilometers, for example. And in TIE GSM, we used, that's the strong Joule heating that provide us the strong local heating in the lower thermosphere. Then it induces large upward vertical wind, then adiabatic cooling above that gave us the strong differential heating. But that's not enough, as I just mentioned. In order to have the narrow structure of TTEIL and large gradients of temperature as shown in the observations, we think that the elevated temperature background, which is simulated by TIE GSM, has to be superimposed by gravity wave perturbations that may coexist at the same time. So after we add the elevated background caused by the Joule heating, triggered by the Joule heating and gravity wave perturbations, that is closer to the observations. So both electrodynamics and neutral dynamics could play a role to finally form up the TTEIL structure. We know that in TIE GSM, currently the methods we use to add electric field variability and Aurora, even though they improve model simulation in general, for example, they solve the problem of underestimation of neutral density to a large extent, and they also give us the temperature enhancement. But inherently, they still have large uncertainties, especially for local region, because electric field variability still is added as a random process, and Aurora linear interpolation sometimes may also miss the realistic Aurora features. So by considering this, we say that we cannot fully rule out other possible heating source, and the Joule heating is one possibility, and we studied this. But how about other possible heating source? Is that also possible, or whether they can work together, or maybe some other scenarios could happen? Then we cannot fully rule out these possibilities currently. and such as the anonymous heating associated with plasma irregularities or heating from wave dissipation could be also studied in the future. So the conclusion is really that we learned something by working on this interesting topic, but there are more to be answered in the future. If you have questions and comments, please send me an email. And thank you everyone for your time in paying attention to this work. And I also want to acknowledge the great support from NSF and the NASA programs. And I want to thank NCAR ASP Faculty Fellowship and also HAO Newkirk Fellowship in supporting my graduate student. Thank you.